Hi everyone, this record is for just in case you have forgotten what we have discussed in the class, and also I did some amendment in our lecture slide. So kindly refer again in my video, and also this will be good for you to do the revision. So and again, what we are going to learn is what we learn this topic is about test of hypothesis. Basically, is for us to do a decision making in research of and engineering. So imagine we have 1,000 of user, and we are now dealing with the big data. So how can we get the feedback of all the population and get the feedback on a product? So what we can do is we try to generalization on the findings by extract the accurate sample from the larger population to reflect the accurate population feedback. And also it can use to quality control, especially in the manufacturing and industrial process. So whether it's inside the rejection region that we have to look for CQI or improvement, or we can still accept our current hypothesis, our current outcome. Okay, next. So what is hypothesis? Is an assumption about an expected occasion. So for example, a manufacturer of a laptop is expecting 99% confidence that laptop produced will have mean lifetime greater than 3 years. So to prove this is correct, we have to, there are two options, whether we reject it or we accept it. But before that, we have to do the hypothesis test. So what we can do is in this case, they random select 500 sample laptop, and then they tested it and to see whether it's really true. So when we need to do a hypothesis test, so we're using the sample characteristic to test the hypothesis about the population. So what we can do is imagine we have thousands of students in UMS, and I would like to know the feedback on the about engineering statistics subject. So whether am I looking for the right sample to reflect the population feedback? So that is important. Okay. So that is, for example, I would like to know the feedback of the students thought about a statistic. So, but I choose a student from social science. Is that same respond from the student from engineering? So we have to think about that. So we have to be careful, select the sample that really best reflect the hypothesis of our population. Next. Okay, so for example, Environment Protect Agent, EPA, want to determine mean level of certain type of pollutant relates to the atmosphere. So in this case, we want to know what is the mean level. So again, we have to decide what is the setting, whether, and then do the test, whether the factory is violating the law. So how we do that? First, we have to set the significant level before the experiment. Second, we have to set the null hypothesis, which is the assumption from the occasion given. The alternative is the one then that the other way around, that we reject the null hypothesis. And then some of the way is you set your rejection region, and then you do the test statistic, or the other way around. So what is significant level? It's you set before the examination. Sometimes you call that as p-value. And if you have significant level less than 1% is highly significant, means that the rejection on the population it's only 1%. Well, for less than 5% is considered significant, and more than 5 is not significant. So therefore, our significant level is between around 1 to 5%. So choosing the null hypothesis, okay, the whole thing under the surface area of the curve, its total probability is 1. So for the alpha part, we always call that as a critical region or rejection region. So in this part, it's where you are not agree on the null hypothesis, whereas the beta is the way the part that you support your null hypothesis, and your null hypothesis is true. So yeah, so there are two way to for the hypothesis testing. Okay, so one is one tail. It could be left tail or right tail. Another one is two tail. So what does that mean is, for example, average age of degree student in FKJ is 23 years old. So your null hypothesis is the mean of the student age is 23. Well, the alternative is the other way around. It's not equals to. So the not equals to could be two way, whether it's less than 23 or more than 23. So in this case, your significant level have to divide it by 2 because you have 2 possibility on each. Whereas if you look at the left tail, your null hypothesis is average age of degree student in FKJ more than 23 years old. So in this case, more than 23 years old, our null hypothesis is more. So our alternative hypothesis will be smaller. Remember in the class I show you, smaller, the arrow is on your left side. So your tail is on the left tail. Okay, so and then for the right tail, average age of degree student in FKJ is less than 23. But your alternative hypothesis will be the other way around, which is more than. So it means that if more than 23, you are going to reject your null hypothesis. So therefore you are having the right tail for the rejection region or critical region. So this is an example. Average mass of bearing is 500 grams. An engineer believed that the weight ought to be different, decided to check out 50 bearings. What is the null and alternative hypothesis? So average mass of a bearing is 500 grams. So we know that the mean is 500 grams. So the engineer belief is different. It could be lesser or more. So therefore, we have two-tailed test in this case. Another example is the manufacturer believed that at least 90% of the new sample passed. The engineer disagreed with the value and decided to conduct a test. At least, so at least is you have might be 90% or more. So your null hypothesis is probability more than 0.8. So because the whole area under the normal distribution, standard normal distribution is 1. So we can convert it into 0.8. Whereas for the alternative is smaller than 0.8. Right. So in this case, we have the left tail. So example number 3 is the student passing rate is not more than 90%. Not more than, in other words, means is lesser or equal. So, but our alternative will be higher. So in other words is, if it's higher, we reject the null hypothesis. So our tail is on the right side. So, yeah. So let's have a look. A chemical plant is producing 100 tons chemical per day. If the mean smaller than 100 ton, the company will bankrupt. If mean bigger, then the financial is safe. To determine whether the production is leading financial disaster, so in this case, it is one tail or two tail. So we have to understand probably to determine whether the production is leading financial disaster. If it's financial disaster, it need to be smaller than 100 ton. So our null hypothesis in this case is smaller than, sorry, there is an error here. Okay. So we change it later. Okay. So this is, okay. Our null hypothesis will be mean smaller than 100. Our alternative hypothesis will be mean bigger than 100. If you're using two-tailed test, means that it could be big, more than 100 or higher than 100. So it will make you hard to define in this problem. Okay? So there are also another way for there are also possibility to have the probability of error. So for example, why this happen is, for example, we have a population like the example that I gave you just now. I would like to know the feedback of the student reflect the statistic, their feedback about statistic. But if I choose the student that from social science about statistic, and I choose student from engineering statistic in mechanical, there must have some changes slightly different on the feedback and cause different mean and different standard deviation, and therefore it can cause some error. So long story short, what you need to understand is the type 1 error is when the null hypothesis is true, you reject the hypothesis. So let's have a look. The null hypothesis is true, it should be beta, right? But you reject it, so it's go to alpha. In other words, means you are actually support the alternative hypothesis. So what you need to remember is alpha support the rejection region, support the alternative. Beta is support the null hypothesis. All right. So let's have a look on one of the example. So for example, an engineer or any job, they say normal day, a service engineer, normal day, it's in a hospital, they work less than 72 hours per week. Whereas for season day, for example, public holiday, the hospital operate very, very busy. So, and they have to work more than 72 hours per week. So they have collected 50 service engineer in that area, the state, and they get the mean and standard deviation. So first they set the significant level is 0.1. Okay, so the null hypothesis, we know that is less than 72. The alternative hypothesis is 72. Okay, in this case, they use they do the test statistic first. So the mean is 74.1 minus 72 over the standard deviation over the square root of 50. With this, you're able to find 1.12. Well, the standard significant level is 0.10. So in this point, you can refer to the table of normal standard normal distribution table. Right, you can get the value for normal distribution table in our IDEX. Let's click have a look. Okay, so our significant level is 0.1. Right, remember this is the table. This is the table. What is the table means is, let's say you have the normal distribution. It's the shaded is respect to the left side. Okay, so for example, when z equals to negative 3.9, it's over here, it's near to 0. So when the z equals to 0, the z is in the middle. The surface area on this part is 0.5. So now, we are looking for the right tail or left tail or right tail. Let's have a look. So our alternative hypothesis is the right tail, right? Or I can flip it to the other side. It's become 0.1. It's a symmetry, right? I show you this. You can also find 0.1. Let me check. 0.1. So you try to find the surface area under here. It's 0.1. Look, have a look. Okay, check it out first. When okay, so I guess this is the closer one. Can you see this? So this is the surface area under, means that what is I mean is here, because our ours is right tail, this is the 0.1, but this is you know it's a symmetry. If I look at the area of 0.1 here, okay, I can have negative 1.28, and also means if my surface area on the right side is 0.1, I can get 1.28. Okay, that will be easier. Is that okay? And therefore, I have the rejection region or critical region is 1.28. So I have my test statistic is 1.12. So in other words means for the conclusion is, I agree that normal day, we support the null hypothesis that the service engineer work less than 72 hours. All right. So what about the sample that are less than 30%? At the condition that the sample less than 30%, quantity, small sample less than 30, we use t-statistic table for our testing. Okay, the difference between the normal distribution table and the standard normal distribution. Okay, let me show you. Okay, the difference is you have the degree of freedom. There is further explanation what is degree of freedom. If you are interested, I can send you the link after this. Okay, in this table, there are two things you need: significant level and degree of freedom. Fair enough. From using this, you're able to find your critical value. Right, so simple, isn't it? So the shaded area on that part is on your right side for the t value. Okay, it doesn't matter. It's the same even for the table that I shared you. Okay, so let's have a look on one of the example whether this is using the t value or using the the standard normal distribution. Okay, let's have a look. Occasional OSHA want to establish whether the level, hypothesis that the level of benzene at a steel manufacturer not exceed 1 ppm. Okay, they tested 20 samples with the mean standard deviation, and they set the significant level as 0.05. So first thing first, we set the null hypothesis, which is less than not exceeds, means less than 1 ppm. Well, for the alternative will be more than 1 ppm. Okay, then our test statistical is the mean, okay, the mean that we collected from the 20 samples minus the mean that the standard we desire over by the standard deviation of the sample divided by the square root of the n. So we get 2.95. So next, we have to set the rejection region using the significant level of 0.05. So the green part is 0.05 for the significant level, and the degree of freedom is 20 minus 1, which is 19. By referring to this table, we know that our critical value is 1.729. So are we fall in the rejection region? No. Yes or no? Yes. So our rejection, the point, it fall in the rejection region. Means that the plant, we are not agree with the null hypothesis that the manufacturing plant not exceed on 1 ppm. In other words, the plant has more than 1 ppm level of benzene. So let's have a look on the next one. A scale to be calibrated is by weighing 1,000 gram test is 60 times. We tested 60 times. 60 scales reading have mean 1,000.6 gram with a standard deviation of 2 gram. The worker disagree with the accuracy of the scale. So by right, the null hypothesis is it should be 1,000 gram. So the worker not agree. So it could be higher or lesser. And therefore we have two tail in this case. So first we set the test statistic 1,000.5 among the 60 scale reading minus the standard one is 1,000 over the standard deviation divided by the square root of 60. Okay, so in other words also, because this is more than 30 samples, we use the standard normal distribution table. Okay, so first, like I mentioned to you, because it's two tail, you have to divide the standard deviation to 0.01 over 2, which is 0.005. So if you look at this, we have to find the 0.005. 0.005. The closer would be 2 negative 2.57. Okay, like I mentioned just now, this standard normal distribution is reflecting the left side. So I'm trying to look for the area under your left side is 0.005, which is 2.57. That is the closest, right? So the negative part is negative 2.57. For the positive side, it will be positive 2.57. So for your test is 2.32. So in other words means because this one is 0 mark. So it's not fall into the rejection region. So we agree that the scale is weighing 1,000 grams. Yeah, we agree with the null hypothesis that the average weighing scale is 1,000 grams. Okay, so all right, so let's have a look the next one. Right, to testing a population proportion, there's another way to test a population. You need to fulfill two parts. Okay, your NP, N is the number of testing, the P is the successful, must be more than 4. And your NQ must be more than 4 as well to testing the population proportion. So for this part, okay, we quickly jump into example. Probably it will be easier for you to understand. Steel collaboration M95% steel bridge in good condition. To test this clamp, 60 bridges are randomly selected and tested. 54 steel bridges are found in good condition. Is there evidence that significant level 0.05, the steel bridge that show good condition, is more than 0.95? So there is a misunderstanding, mistake in the lecture slide, but when we look at this, the null hypothesis is more than 0.95, whereas for the alternative is less than 0.95, right? Our null and alternative set. So next, we know that this is a one tail and this left tail test. So by looking for the significant level, and this is more than 30, we are using the normal standard table. Okay, so we get negative 2.57. Now, we have to find again our sample proportion. Okay, so in this sample, this can only have binomial outcome, success or not. So our new successful probability is from the 60, we can have 54 over 60, which is 0.9. So next, we check whether we can use this equation. So NP, when you times it together, it's more than 4. And Q is also more than 4. Right. So next, we find our test statistical, and we found that ours is negative 1.78. So it's not inside the rejection region, and therefore we support our hypothesis, okay, that it's more than 95% are in good condition. Okay, so besides that, we also have another thing called chi-square distribution, when you would like to get relationship between two categorical variables. What that mean is, for example, what is the relationship between preferred engineering course and the degree student enter? So they are in categorized variables. There are two assumptions for this when you use the chi-square. Your expected frequency must be greater than 5. So your frequency shouldn't be less than 5 times. Your chi-square test only for categorical, not ranking. Ranking means, for example, what is the relationship between the student qualification level? That's ranking. Then you use another part, all right? For the chi-square, you have it basically still have the same thing. You have one tail or two tail, but the equation would be slightly different. For this one, normally you have two tables. One is the observed, one is the expected. So the OI is observed frequency. The E is the expected value that we're expected for example, you set it. So this is a chi-square table. The chi-square table is quite similar to the t-student table, but the difference is if you refer back to the t table, okay, the t table, if you look at this, is on the right side shaded. Okay, for the chi-square is also at the right side one. So let's have a look on this, an example. Let's say we have 4 machine, and to come up the pin, to test the pin, the proportion of pin that are too thin, okay, or too thick are the same for all the machine. So our null hypothesis. And we also said that the wait. So first, our significant level, let's say we set it as 0.01. Okay. So you might question in this part, okay, do we need to divide to 2 for the chi-square? Because it say that the proportion are all the same. Or you can have 2 parts, which is either too much or too right. So first we try to find the chi-square value by 2 thin minus the, as observed, minus the expected power of 2 over the expected. So you can refer to the equation here. Okay. For chi-square, so if you refer to the chi-square table, okay, so it's 0.01, and the degree of freedom, because this is in a table form, what you can do is, remember degree of freedom is always -1. So the number of machine is 4, you -1 times, there are 3 category, 3 minus 1. So total you have 6, and therefore you have 16.82. And by using the chi-square, you have 15.54. And therefore, in this way, means it's not fall under the rejection region, and therefore we agree our null hypothesis level. Right. So that's all for now. If you have any question, please drop me a message. Right. Thank you, everyone. Bye.